Welcome to AI Frontiers. Today, we're exploring the forefront of robotics with a selection of 31 recent research papers from December 21, 2025. This episode provides a journey through recent robotics research papers, uncovering key themes driving innovation, highlighting groundbreaking findings and methodologies, and offering a glimpse into the future of robotic systems. Computer science robotics involves designing, building, programming, and deploying robots. It blends mechanical, electrical, and computer science with artificial intelligence, creating machines that sense, think, and act. This field transforms manufacturing, healthcare, logistics, and exploration. One research theme focuses on multi-agent systems and swarm robotics, coordinating large groups of robots to tackle complex tasks through collaboration. The development of algorithms for communication and collision avoidance is critical. Warnikulasauria et al. Focus on efficient swarm coordination. Another theme involves localization and mapping, enabling robots to understand their position and surroundings. This requires developing algorithms and sensor systems for accurate mapping, crucial for navigation in dynamic environments. Peng et al. Integrate localization and planning for efficient navigation, while Perez-Ruiz et al. Improve litter inertial odometry systems. Dexterous manipulation and grasping are also a core focus. This involves developing algorithms for grasping and manipulating objects, enabling robots to generalize their grasping skills. There is an active effort in bridging the gap between simulation and reality, known as Sim2Real. Wang et al. Explore hand-object tracking from synthetic data, and Fan et al. Present TwinAligner for improved zero-shot transfer. Further research focuses on autonomous driving, developing algorithms for safe and efficient autonomous vehicle navigation, with safety and robustness being paramount. Vision language models, or VLMs, are also emerging, enabling natural language robot instruction. Liu et al. Propose data pruning for efficient autonomous driving training, and Guo et al. Propose MaP-AVR for embodied robotic AI systems. Key findings include the successful deployment of AI-based control systems in real-world environments, demonstrated by Djebko et al. Data-efficient learning techniques are accelerating robotic skill development, as shown by Zhao et al. Vision language models are transforming human-robot interaction, exemplified by Guo et al. Navigation without explicit mapping is progressing, demonstrated by Peng et al. And closing the sim-to-real gap is becoming more achievable, thanks to efforts like Fan et al. The methodologies behind these findings include reinforcement learning, where robots learn through trial and error; imitation learning, where robots learn by watching expert demonstrations; sim-to-real transfer techniques, which bridge the gap between simulation and reality; and optimization-based control, which formulates control as an optimization problem. One selected paper is Djebko et al.'s LAR. The first in-orbit demonstration of an AI-based satellite attitude controller. This showcases the successful real-world deployment of deep reinforcement learning in space. It achieves robust attitude control using an AI agent trained entirely in simulation. A deep deterministic policy gradient, or DDPG, algorithm and domain randomization enable sim-to-real transfer. The AI-based controller performs robustly during repeated in-orbit maneuvers, including inertial pointing maneuvers. Another selected paper is Peng et al.'s LoGoPlanner, localization-grounded navigation policy with metric-aware visual geometry. This integrates localization and planning into a single framework, achieving accurate navigation without relying on separate localization modules. Metric-aware geometry memory enhances planning consistency and obstacle avoidance. It outperformed Oracle localization baselines by more than 27.3%, with the potential for greater generalization across different robots and environments. Finally, there is Fan et al.'s TwinAligner. Visual dynamic alignment empowers physics-aware Real-2 Sim2Real for robotic manipulation. This addresses both visual and dynamic discrepancies between simulation and reality, creating a visually and dynamically realistic simulation environment. A visual alignment module reconstructs scene geometry, and a dynamic alignment module ensures dynamic consistency. Policies trained in simulation achieve strong zero-shot generalization. Future directions in robotics include further bridging the sim-to-real gap, developing more data-efficient learning algorithms, addressing the ethical implications of increasingly autonomous robots, developing robots aligned with human values, and focusing on robot safety. This synthesis was created using AI tools, including GPT, Google using models, Gemini 2.0 Flash for text generation, Google for TTS synthesis, and OpenAI for image generation. A human expert reviewed the content for accuracy. Potential oversights may exist. References are provided. AI enhanced efficiency and synthesis, and the tools accelerated the development of high-quality content. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprintserver.org.